First, I'd like to thank Hugo and I'm sorry, your name again, Jose?
Yeah, Jose, yeah.
Jose and Hugo for today and talking to us about active dry yeast. And this is a topic that we've all been interested in. Many of us rely on dry yeast, be it through Fermentis, Almond, Mangrove Jacks. A lot of people still use liquid yeast, but it's something that I've crossed over to dry yeast over the last couple of years, just for the ease of it and how accessible it is. So looking forward to the presentation, and hopefully we can get some good conversations going on from this. So thanks, you guys, and I'll hand it over to you.
Perfect. Thank you very much, John. So just to introduce myself, I'm Hugo, and I'm in charge of all the home segment for Fermentis. I have a master in agronomy, and I joined Fermentis since more than 2 years now. And with me today is Jose, who is in charge of the eastern area of the US and Canada for the craft segment, so more for the professional brewers. And today the idea is to talk about active dry yeast and to present the basics of this solution during approximately 45 minutes. And after, simply do a Q&A session to talk about all the topics and questions you could have regarding this subject. So first of all, I would like to thank Breven, Hambrook, and John to give us the possibility to talk with you today. It's something we have started almost 1 year ago to be in touch with all the Hambrook and to talk with true people, true homebrewers in direct, and give you our feelings about fermentation and yeast. So thanks again for this possibility to talk with you today. Here you can see what we will present today. First, a focus on the production and drying process. We will do an overview of the manufacturing process with a focus on propagation and drying. And we will also review all our quality procedures. In a second time, we'll have a look to a shelf life study we have conducted through a forced aging test and natural aging test. And of course, the conclusion we have of these 2 studies. And finally, we'll have a look to a rehydration, viability and vitality study to speak about what we call our easy-to-use concept. In the first time, we will review rehydration and direct pitch procedures. After that, we'll see the impact of rehydration conditions on yeast cell viability. And finally, the direct pitching impact on yeast cell vitality. And the conclusion after that. So let's start first with the production process. What you see on this slide, it's basically how we produce yeast here in Le Saffre and Fermentis. Everything's come from our R&D department at the beginning. The strain is in what we call a cryotube, stored at minus 80 degrees C, minus 112 degrees Fahrenheit. And we send this cryotube to our factory located in Belgium. It's called Algist. And we have here a first step in laboratory. It's a first step of multiplication. And we start from volume of 250 milliliters to a volume of, let's say, 3 liters. So all this part here is done in laboratory under totally sterile condition. After that, we move from the laboratory step to a true factory step, if I can say that. Here, the idea is that we do this multiplication step in big tank and then larger tank and then larger tank. It's what we call the step of propagation. So here we want to produce biomass. So of course we need sugars, but also vitamins, trace elements and nutrients to feed the yeast, but also oxygen to let the possibility to the yeast to multiplicate. It's really what we want here. And if we do a focus on what happened inside the fermenter, it's basically that. What you can see there, it's the yeast duplication in the fermenter, and this scheme, it's the scheme of replication of a yeast cell. So we start at the bottom. First, you will have the replication of the DNA, the migration of the DNA to the two extremities of the cells, and finally the division of the cells itself in two daughter cells genetically identical. It's how we propagate the yeast and we multiplicate. And after that, we stop the division cycle when a wide majority of the cells are not budding. Why? Because it's increase the viability of the yeast after drying, meaning that when you will put again the yeast in your wort, the yeast will be totally ready to work and to assimilate sugars. It's what you can see right there. So we like to say that the doors are open for sugar assimilation. So as soon that you will put the yeast in your wort, the yeast will start to work. It's the reason why we say that the active dry yeast is the freshest yeast format. So if we continue in this big production process, we have now enough biomass of yeast. So we continue in the process. And what we want is to remove all the water. So we will use a centrifugator. On one side, you will have wastewater. And on the other side, you will have a kind of yeast cream that would be stored at 4 degrees C. This yeast cream will be sent on a vacuum filter, you can see right there, to create a kind of pasta, yeast pasta. And finally, this pasta will be sent on a fluidized air bed. In fact, it's a specific technology to dry yeast with hot air. It's what you can see there. And at the end, you have the yeast you can see in all the sachet you can buy. And if we have a look at the microscopic scale, what happens when we dry the yeast is that, so before drying, you have around 25 to 30% of dry matter and a totally smooth cell surface. And after drying, you have between 94 and 96% of dry matter and an uneven cell surface. So now you know in the big lines how we produce yeast at Fermentis. But what is really important for us also is the quality of what we produce. And it's what we are going to see now. We really want to deliver and to give you the possibility to work with the best quality as possible. It's the reason why we have a big procedure to control this quality. In fact, when we select a new yeast strain in a specific database or anywhere, you have a first step of quality control regarding genetic purity and all the properties of the strain. If the control are good, this strain is added to what we call the LOSAF yeast collection R&D, meaning that our R&D team will work with this strain to know for which application it's the best. It could be beer, of course, it's the topic of tonight, but also wine, bread, or many others. Once they have selected the best application, you have a second battery of tests, of quality tests, always regarding genetic purity and properties. It then propagates to arrive in what we call the industrial collection of Le Saf, meaning that this yeast strain is ready to be propagated and go in the factory. For that, we need to propagate again, and you have a third quality control, always the same than the two previous ones. And you arrive finally at the daughter line yeast tubes you have seen in the production process at the beginning. It's the tube stored at -80 degrees C. It's the tube that we will send to the production plant. And before to be sent, we do another quality control, this time only based on genetic and properties of the strain. After that, so we have the same step that you have seen before in the production process. So with the reception of the yeast tubes by the production plant, all the laboratory phase when we will propagate the strain. Before to move into the big fermenter you have seen, you have always a new purity control. You have than before, and the most important control is there. So the yeast is produced, ready to ship, but before that we ship anything, we do a last quality test regarding the purity, the composition, aging, and all the properties to say that, okay, this yeast is ready to go, ready to be sold, and it's the best quality you could have. If we don't have this positive quality release, we not sell the yeast. So finally, you know right now that you always work with the best quality yeast. So, okay, you know how we produce the yeast, you know that the quality is good. One question could be how you can store it at home. And it's what we will see through this shelf life study. So to know for how long you can keep this yeast at home, we have done the following study. So the idea is to compare the results between a fresh active dry yeast and aged active dry yeast. So it's a forced aging test, meaning that we have simulated aging by exposing the yeast to a specific temperature for a specific amount of time. You can simulate natural aging. So we have established a protocol where fresh yeast is exposed to elevated temperatures for a specific amount of time, and that is the equivalent of 1, 2, 3, or 4 years of natural aging. And the idea is to compare the results regarding fermentative power, viability, and the end of fermentation compounds like residual sugar, volatile compounds, and to see if we have any difference between a fresh active dry yeast or an aged active dry yeast. So first, here we are on all our ale strains. So it's all the yeast you know under the SAF Ale brand. So SAF Ale USO5, SO4, K97, etc. On the left, what you can see is the fermentation times, so in days simply, and on the right, the fermentation rate, so it's the ethanol produced per day. And you have the color code just right there. So to simplify the reading, I have only put the results for 4 years of forced aging. You don't have here the 1 year, 2 years, 3 years. But what you can see is that between the two conditions of fresh or aged active dry yeast, you don't have any significant difference for the aged strain. It's the same number of days of fermentation and the same rate for fermentation. And it's true for all our strains. So no significant difference. If we now have a look to the specific compounds, we are still on the ale strain. You see that, again, we don't have significant difference. So here you have the esters produced, so ethyl acetate, isoamine acetate, etc. Here's the total ethanol produced, and here the higher alcohol produced. So higher alcohol and ester are explained here in ppm. ppm means part per million. It's a unit used in chemistry to express a mass fraction. Please note that the scale of this graph and this one are really, really small. So maybe you can see some differences between the two columns, like there, but it's very a small difference. So for example, in the case of the K97, between the fresh K97 and the aged K97, you will have a difference of 0.1 ethanol percent of ethanol. So it's really nothing. So again, we can say that we have the same results between a fresh active dry yeast and aged active dry yeast. If we now have a look at our lager strain, so it's all the strain you know under the brand SAF Lager, so S23, W3470, and S189. So here you have all the results on the same slide. At the top left, the ethanol, the total ethanol produced. At the top right, the ester produced. At the bottom left, the fermentation rate, and finally, the higher alcohol produced. So again, I remind you that keep attention to the scale. It's really small scales, and what you see is that we still don't have any significant difference between the fresh and the 4 years first age active dry yeast. So okay, we have seen there that we don't have any significant differences in all cases, but it was simulated aging, so it's not really true. We agree with that, so we did the same study but with natural aging. So during 44 months, we have kept the yeast at different temperature. So minus 20 degrees C, it's minus 4 degrees Fahrenheit. 5 degrees C, it's 41 degrees Fahrenheit. And 25 degrees C, it's 77 degrees Fahrenheit. So we keep this yeast at these three temperatures during 4 years, and again we compared the results of fermentation. So here you have an example of ale strain. It's a case of SAF Ale SO4, but it's just an example. But be ensured that the results were consistent with all our strain. You can see that for the fermentation kinetics, so here you have the extract in degree plateau, and here the time in days. you have the same kinetics between the fridge batch and the 3 different age active dry yeast at the 3 different temperature. It's almost the same kinetics, and we can say that the fermentation is over after 5 days, so no significant differences. In the case of the lagers, it's a bit different. So here you have the example of the SAF lager W3470. And here you see that we have a difference regarding the kinetics. So it's another way to present the kinetics, because here we have the apparent degree of fermentation in percent, and we still have the days at the bottom. The fresh active dry yeast is there, so we can say that more or less the fermentation is finished after 8 days. It's the same case for the yeast age at minus degree 4 and 41 degree Fahrenheit. But in the case of the yeast stored at 77 degree Fahrenheit, the fermentation is over after 12 days. So we have a difference in this case. But keep in mind that it's really an extreme condition. Normally, you don't have to store an active dry yeast during 4 years. I hope you use it before that. And on top of that, at 77 degree Fahrenheit, it's really extreme. So what we can conclude of these 2 studies is that we don't have significant differences between fresh and aged active dry yeast. And it's the reason why we can recommend 3 years of best before end date for ale brewing yeast, and the same for lager brewing yeast. So why 3 and not 4 years? It's just because of the slide you have seen there. After 4 years, we have seen that for lager strains, we could have some differences. So we made the choice to be consistent for all our strains, and not say 4 years for ale strain and 3 years for lager strains. And to the storage at cool and dry condition, and it's more than recommended if you want to keep the yeast for a long amount of time. So now you know how to store your active dry yeast, but at one moment you have to use it. So we will see now what is the best method to use active dry yeast. Just a reminder, viability is simply mean that if a yeast cell is dead or alive, and vitality is simply the energy of the yeast cell will have to work. Remind that yeast is an alive organism, so it's the same than people. You have some yeast with more energy than others. So the first method we know to use active dry yeast is with a radiation procedure, meaning that you will add your yeast to 10 times its weight of water or wort, depending of what you prefer. Leave to rest for around 15 minutes or sometimes more. Stir gently, and only after that, pitch this yeast cream in the fermenter. It's the first school. And the second method is the direct pitch, the easiest method. So simply start to fill your tank cone, sprinkle the yeast slowly on the wort surface, and complete the filling with wort at fermentation temperature. So on the forum, like Homebrew Talk and many others, you always have guys that say you have to rehydrate to have better result, or direct pitch, it's okay, you can go like that. And it's what we will try to explain right there. What is the best method? So first, we'll have a look of the impact of rehydration on yeast cell viability. To do that, we have put in place a specific protocol. And here the idea is to rehydrate dry yeast in 10 times its weight of different media and with different parameters. The first parameter we will play with is the time. So we will do a rehydration of 15 minutes, 25, 35, or 45 minutes. The second parameter is the agitation. We will do without any agitation, so just the yeast placed on the liquid surface and the rehydration completed without agitation at all. Moderate agitation, the yeast will be placed on the liquid surface and no agitation for 15 minutes, and then agitated at 100 rotations per minute. And violent agitation, the yeast will be placed in a sterile flask, medium poured on the yeast, and a violent agitation applied every 2 or 3 minutes. The third parameter is the temperature. We will do different rehydration at 46, 54, 61, 68, 90, and 104 degree Fahrenheit. And finally, the last parameter is the media. So 3 types of water: distilled, mineral, and tap water, and 3 types of wort: 7 degree P, 15 degree P, and 25 degree P. And to measure the viability, we will do what we call trypan blue exclusion test. It's simply a product will go inside the damaged cells and color them in blue. Like that, when we look at the microscope, we're able to see the percent of cells which are dead. And so we have the viability in percent. So let's have a look to this result. First, what you can see here, it's the case of 3 ale strains, so T58, USO5, and S33, yes. And what we want to have a look is the influence of temperature and agitation on viability. You have the color code here. So in blue, it's without agitation. In red, it's medium agitation, and in green, it's violent agitation. What you can see is that we always have the best cell viability, so in percent, as explained before, without agitation, and it's the case for the 3 ale strain. Of course, the viability is different from a strain to another because we have more or less sensitive strains. So really, it seems to be that without agitation, it's the best method to rehydrate. And another interesting result is that higher temperature seems to be preferable to rehydrate. In the case of lager strains, so again, we study the temperature and the impact of temperature and agitation. We have exactly the same result. So here you have the S23 and on the right the S189. And again, without hesitation, you still have the best percent of cell viability. If we now have a look of the influence of rehydration time on viability, For that, we have fixed two parameters. So we have a moderate agitation and a temperature at 90 degrees Fahrenheit. On the left, you see 3 examples of ale strain, and on the right, 2 examples of lager strains. And what we measured is that the best percent of viability is reached after 15 minutes of radiation. It doesn't seem to be necessary to take more time to rehydrate, because the results are consistent after that. You still have the same percent of viability when by increasing the time. Sorry, so it's not necessary to spend so many times to rehydrate. 15 minutes is more than enough, and you see that it's true in both cases, ale strain or lager strains. A new parameter we study is the radiation medium. So here is the type of water. We have again fixed the parameters of agitation. So we have moderate agitation and temperature of 90 degrees Fahrenheit. And you have the example of 2 ale strains, so the T58, the US05, and the US05, and the example of the S23. In blue, it's radiation in distilled water, in red in mineral water, and in green in tap water. What we can conclude of that is influence viability during the radiation. And in fact, when we combine all the condition, we have a viability which varies from 75 to maximum 95%. And if we now have a look, we are still on the radiation medium, but here with wort of beer. So 3 types of wort: 7 degree P, 15 degree P, 25 degree P. And we have the water for reference, and the same 3 strains. We see that again some conditions are still fixed, the agitation, and we are still at the same temperature, so 68 degrees Fahrenheit, 20 degrees C, and 45 degrees Fahrenheit. So yeah, here we can conclude the same. In fact, it's just that the sugar concentration does not significantly influence viability during radiation. When you take the different strain, you see that if you take wort at 7 degree plateau, 15 degree plateau, or 25 degree plateau, you don't have a huge difference in terms of viability. And now, if we have a look to the other side, so we have seen the impact of radiation on the yeast viability. Let's have a look to the impact of direct pitching on yeast cell vitality. For that, we have a new protocol. So on the left for ale strains and on the right for lager strains. In the 2 cases, we have studied 3 strains, and we have studied 3 radiation conditions or process of use for the yeast. The first is radiation in water at 30 degrees C with a moderate agitation. It will be symbolized in the following slide by a W. The second method is a radiation in a 15 P wort at 30 C with a moderate agitation. It will be symbolized in the following slide by 15 P. And finally, no radiation at all, which is the equivalent of direct pitching, which will be symbolized by the DP in the next slide. So it's the same for lager strains. We have a standard wort at 15 plateau. The pitching rate is 50 grams per hectoliters for ale strain and 100 grams per hectoliter for lager strains. The temperature fermentation, it's classic for ale, 68 Fahrenheit and 57 Fahrenheit for lagers. To be sure, we have repeated a forced aging test, meaning that we have seen that you don't have significant difference between fresh and aged active dry yeast, but we just wanted to be sure that it's still the case if you use the yeast in different conditions, meaning with direct pitch or a prior radiation. So we will study that too. How we will do the follow-up, we have done the follow-up and analysis. From one side, we have analyzed the fermentation performance by different tests in triplicate. First, we have evaluate by measuring the decrease of weight of the medium, and also the correlation to the sugar conversion into CO2 and ethanol. And from another side, we have done analysis realized at the end of fermentation by HPLC. HPLC simply means high performance liquid chromatography. It's a technique in analytical chemistry used to separate, identify, and quantify each component in a mixture. And the component we want to study is what you can see there, so ethanol, acetaldehyde, ester, etc. And let's have a look to these results. So here you have the case of an ale strain, so the SAF ale, US05, you all know. On the top left, you have the kinetic of fermentation. Top right, the total ethanol produced. Bottom left, the apparent degree of fermentation. And bottom right, all the volatile compounds. So for the color code, it's the code I just explained before. So W, it's radiate in water, 15 P, it's radiation in wort, and DP, it's for direct pitching. So the idea is always to compare these three different conditions. You see that for the kinetics, we always have the same kinetics. It doesn't matter if you radiate or if you direct pitch. For the ethanol produced, you don't have any significant difference also. The same for the apparent degree of fermentation, and still the same for all the volatile compounds produced. So we have the VDK, the higher alcohol, the esters, and the acetaldehydes. So finally, for this example of ale strain, I only show you the example of SAF ale US05, but the results were consistent with the other strains. We will always have the same results in terms of fermentation for our ale strains. And as I said before, we just wanted to be sure that we have the same results between aged active dry yeast and fresh active dry yeast. So you see the kinetics of fresh active dry yeast and the kinetics of aged active dry yeast, and you see that you have no difference between the two types of yeast, and doesn't matter the way you use the yeast, so direct pitching, radiation.
All right. Well, I think I'm going to take over Hugo. I apologize for that. By doing all these kind of online stuff, there is always glitches, like always. So I'm going to I'm going to give up on the chat, as it's hard to be on the two sides at the same time. And I'm going just to keep going through Hugo's slides. So I was not active listening what he was saying, so I will take the slide from the beginning. Oh, yeah, sorry, as John says, it's a good chance to refill the glass. I was talking with Hugo, he's telling me that on his side, like, he's doing the presentation and moving through the slide, and I was like, well, we lost you over this side of the Atlantic. So I'm going to do this slide until he reconnects, and he will catch up with us in a couple of minutes. So what you can see on the slide here, let me take the pointer.